Okay, so basically after definition number 13, which was about it's called the basic, which was about given a binary operation star on set A, that is a binary star as a binary operation on set A, an element E belonging to A, if it exists, is called the identity for the operation star. Is called the identity for the operation star if A star E is equal to A is equal to E star A. And as an example, we had this example of 0, and the binary operation was addition, meaning that A plus 0 is equal to A is equal to 0 plus A, right? So this is what we had in the end of the last video. And so now as an example, we have example number 38. We have example number 38, which is show that 0 is the identity for addition. You want to show that 0 is the identity for addition on R, the set of real numbers, and 1 is the identity for multiplication, and 1 is the identity for multiplication on R. But there is no identity element for the operations there is no identity for operations subtraction as a binary operation on R, and division as a binary operation on R. Now the solution here is that basically about 0 being an identity for addition on R, 0 being an identity being an identity for addition, identity for addition on R. So you have 0 plus A plus 0 is equal to 0 plus A is equal to A. And also you know that A times 1 is the same thing as 1 times A is the same thing as A for all A belonging to R. Implies that this implies that 0 and 1 are identity elements. 0 and 1 are identity elements for the operations addition and multiplication respectively. Further, there is no element E in R no element E belonging to R with A minus E, with A minus E is equal to E minus A is equal to A, that simply doesn't exist for all A. And similarly, we cannot find any element E in R plus, in R star. That's supposed to be R star. So this is supposed to be, division is on R star only. Further, basically similarly, we cannot find any element E in R star. We cannot find any element E in R star such that A divided by E is equal to E divided by A, such that A divided by E is equal to A divided by A for all A in R star. And so hence subtraction and division do not have identity elements. Do not have identity elements. Now, as a remark, what we can say here is that as 0 is identity for addition operation on R. 0 is identity for the addition operation, on R, but it is not identity for the addition operation on N. But it is not identity for the addition operation on N, as 0 does not belong to N. So so we said that if 0 has to be the identity operation for take a look at. So basically, as a definition, we said that given a binary operation star on A, an element E belonging to A, if it exists, is called the identity for the operation star. If A times E is equal to, if A star E is equal to A is equal to E star A. Now 0, we said that if, so let me write down the definition number 13 one more time. Definition 13 one more time. and that is given a binary operation, star on A, meaning that if star is a binary operation on R, or on A basically, or on A, an element E belonging to A, if it exists, is called identity for the operation star, if A star E is equal to A is equal to E star A. Of course, for all A belonging to A, right? So this was the definition that we had, and so based on this definition, what we can say is that, well, of course, 0 is identity for addition operation on R, but it is not identity for the addition operation on N, as 0 is basically, the 0 does not belong to N, meaning that, for example, if you write 1 plus 0, if you write the identity for addition on R, but it's not the identity for addition operation on N. Well, of course, to understand this statement, of course, you know that 1 plus 0 is equal to 1 is equal to 0 plus 1, right? So that means that 1 is equal to 1 is equal to 1, and this statement is true. But the problem is that 0 does not belong to N in the first place. That means that, which means that, and here we are saying that if it exists, and it doesn't and 0 basically doesn't exist in the first place in N, and so it's not an identity operation on anything in N, not multiplication, not division, not subtraction, and so on and so forth, right? So that is that. And so, as a remark, we said that 0 is identity for the addition operation on R, but it's not identity for the addition operation on N, as 0 does not belong to N, right? And in fact, the addition operation on N does not have any identity. So here we have, in fact, the addition operation on N, does not have any identity, right? So what that means is that there is no such number in N, such that there is no such number E is in E belonging to N. There is no such number e belonging to n such that e plus a is equal to a plus e. It just doesn't exist because the only number that could basically fulfill this condition would be 0, and 0 is just simply not there, and so this number simply doesn't exist. And so that is basically that. And you can say that one further notices that for the addition operation, meaning addition as a binary operation on R, given any a belonging to R, given any a belonging to R, there exists negative a in R. There exists negative a in R such that a plus negative a is equal to 0. A plus negative a is equal to 0. Which is equal to 0, which is the identity for addition. The identity for addition, which is equal to negative a plus a, right? So a plus negative a is equal to negative a plus a, which is equal to 0. So and similarly for multiplication operation on R, similarly for multiplication operation on R, given any a not equal to 0 in R, we can choose 1 by a in R such that a times 1 by a is equal to 1, which is the identity for multiplication. The identity for multiplication, which is equal to 1 divided by a times a. This leads to the following definition. This leads to the following definition, which is definition number 14. Definition number 14, which is given a binary operation star on A, and I did make a mistake somewhere over here. When I was defining a binary operation on A, I wrote an R over here, which is supposed to be an A, of course. So I apologize for that. I saw that, and later, of course, once I was reading my own text, and so I have to basically take care of that, or basically correct myself. And there we have the definition number 14. Okay, so definition number 14 is given a binary operation star on the set A. So you have given a binary operation star on the set A. Binary operation star on the set A, meaning that A, the Cartesian product of A to A, with the identity element A in A, with the identity, I'm sorry about this, with the identity element E in A, an element A belonging to A is said to be invertible. An element A belonging to A is said to be invertible with respect to the operation star. So with respect to, you can write it as with respect to. With respect to the operation star, of course, this is some Indian thing. I mean, usually, I have seen this in India. So, but you know what I mean by this. With respect to the operation star, if there exists an element B in A, if there exists an element B in A, in such that A star B is equal to E is equal to B star A, and B is called the inverse of A and is denoted by A inverse, and B is called the inverse of B. The inverse of B is called the inverse of, this is the inverse of A. The inverse of A, and is denoted by A inverse. So where this definition comes from is basically from this example. Let's take a look at the example that we had before, because I actually don't have any context to understand this completely. So here we are saying that given a binary operation star on A with the identity element E in A, meaning that if the identity element E does exist in A, an element A belonging to A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to E is equal to B star A, and then if that is the case, then B is called the inverse of A, and is denoted by A inverse. So now the context that we need for this definition is basically, let's go back over here. So we had a problem over here, and basically was example number 38. We said that show that 0 is the identity for addition on R, and 1 is the identity for multiplication on R, but there is no identity for operation subtraction and division on R and R star, right? And so 0 being, so we said that basically 0 plus A plus 0 is equal to 0 plus A is equal to A, and A times 1 is equal to 1 times A is equal to A for all A belonging to R. And so that implies that, this implies that 0 and 1 are identity elements for the operations addition and multiplication respectively. And furthermore, there is no element E belonging to R with A minus E is equal to E minus A is equal to A for all A. Similarly, we cannot find any element E in R star such that A divided by A is equal to A divided by A divided by E is equal to A divided by that is actually supposed to be equal to E divided by A for all A belonging to R star. Hence, basically subtraction and division do not have identity elements. And as a remark, we said that 0 is the identity for the addition operation on R, but it's not that the identity for the addition operation on N, as 0 does not belong to N. 0 was not simply there. And in fact, the addition operation on N doesn't have any identity. And then we had another definition that said that basically, given a binary operation star on A, an element E belonging to A, if it exists, is called the identity for the operation star if A star E is equal to A is equal to E star A for all A belonging to A, right? And then we said that there is no such number E belonging to N such that basically E plus A is equal to A plus E, and this was a part of a remark that we were talking about, and one further notice is that for the addition operation, given any A belonging to R, there exists negative A in R, such that A plus negative A is equal to 0, and negative A plus A is equal to, again, the same thing, 0. Similarly, for multiplication operation on R, given any A not equal to 0 in R, we can find 1 divided by A in R, such that A times 1 divided by A is equal to 1, which is the identity for multiplication, and 1 divided by A is equal to 8. This leads to the following definition. And the definition that we have here is that given a binary operation star on A with the identity element E in A, and element A belonging to A is said to be invertible with respect to the operation star if there exists an element B in A such that A star B is equal to B star A is equal to E, and B is called the inverse of A and is denoted by A inverse. So we can use basically for example, you can use the information that we can use the information that we have here, which says that give one further notices that for the addition operation, basically there exists a negative a in R such that negative a plus a is equal to 0 and a plus negative a is equal to 0. Both of them basically in both orders is equal to 0, which is the identity for addition. So then you can say that negative a is the inverse of a with respect to addition in R, and also you can say that a is the inverse of negative a with respect to the operation of addition in R. So that's basically what it means, meaning that, for example, if you take a as 2, then there is a negative 2. 2 plus negative 2 is equal to 0, negative 2 plus 2 is equal to 0, and 0 is the identity for addition in R. So then you can say that 2 is the inverse of A, and you can call it 2 inverse, for example. Or negative 2, you can call it the inverse of 2, the inverse of negative 2, and that's 2 negative, that's well, the inverse of negative 2 in R, right? So that's basically definition number 14. That is definition number 14. Now let's do a couple of examples. There is only example number 39 and 40 here, and after that we will have some exercises. So let's just take a look at these examples here. So example number 39. Example number 39. What we have is that show that negative a is the inverse of a. Show that negative a is the inverse of a for the addition operation or basically the addition operation on R, and 1 divided by a is the inverse of a not equal to 0, and 1 divided by a is the inverse of a not equal to 0 for the multiplication operation. For the multiplication operation. Or basically the multiplication operation on R, right? Now, you know that basically as the solution we can say that for the solution we can say that as a plus negative a is equal to a minus a is equal to 0, and that is equal to negative a plus a, right? Negative a is the inverse of a for addition. Negative a is the inverse of a for addition. And similarly for a not equal to 0, a times 1 divided by a is equal to 1 divided by a times a, implies that implies that 1 divided by a is the inverse of a for multiplication. And that's basically the solution is pretty simple. And as another example here, example number 40. Example number 40, we have show that negative a is not the inverse of a, is not the inverse of a belonging to n for the addition operation on n or the addition operation on n, and 1 divided by a is not the inverse of a belonging to n, and 1 divided by a is not the inverse of a belonging to n for multiplication operation for the multiplication operation on basically on n for a not equal to 1. Okay, so to understand the question, what we are saying here is that we want to show that negative a is not the inverse of a belonging to n for the addition operation, because basically then e would not belong to n, meaning that if I write a plus negative n, negative a, that gives me 0, and 0 does not belong to n. So negative a is not the inverse of a belonging to n for the addition operation on n. And 1 divided by a is not the inverse of a belonging to n for the multiplication operation, because, for example, and of course provided that a is not equal to 1. For example, if a is equal to 2, then 1 divided by 2 times 2 is equal to basically 1, and that is equal to 2 times 1 divided by 2, so we have no problem here. But if a is equal to okay, so what we want to show is that and 1 divided by a is not the inverse of a belonging to n for the multiplication operation on n. Okay, so the second part I don't understand it, or at least I don't understand how to solve it, which implies that I don't understand it, the question. So the question is 1 divided by a is not the inverse of a belonging to n for the multiplication operation on n, for a is not equal to 1. Let's see. Okay, so basically, well, I didn't understand the second part of this question, and then what I realized was that I hadn't understood the definition properly, meaning that it says that for the addition operation on n, and 1 divided by a is not the inverse of A belonging to n for the multiplication operation on n for n not equal to 1. So why that is true is that basically suppose that and that basically the reason why that is true is based on the definition itself. We said that the definition, let me rewrite the definition 14. Definition 14, and the definition 14 is basically given a binary operation star on set A, given a binary operation star on set A, meaning that the Cartesian product of A and A to A with the identity element E in A, with the identity element E in A. So that means that first of all, basically the binary operation. So first of all, we have a binary operation star on A, and E does exist in A, of course. So if the and that E does exist in A, so that is basically one thing. And an element A belonging to A is said to be invertible. An element A belonging to A is said to be invertible. Is said to be invertible with respect to operation star. With respect to operation star, if there exists an element B in A, if there exists an element B in A, capital A, such that A star B is equal to E is equal to B star A. And B then is called B is called the inverse of A and is denoted by A inverse, right? So what that means is that so first of all, the binary operation star, we have a binary operation star on A with the identity element E in A that exists. The identity element E in A, it does exist. And of course that is with respect to, and that is of course with respect to the operation that we have here. Now an element A belonging to A is said to be invertible. Any A belonging to the set A is said to be invertible with respect to the operation star. If there exists an element B in A, so B has to exist in A such that A star B is equal to E is equal to B star A, and then B is called the inverse of A and is denoted by A inverse. Now in this problem here, what we have, the situation that we have is that the situation that we have is that the situation that we have here is that basically we are saying that and 1 divided by A is not we want to show that 1 divided by A is not the inverse of a belonging to n for the multiplication operation on n, for basically a is not equal to 1, for a is not equal to 1. Now, of course, if a is equal to 1, then 1 divided by a is also equal to 1. And then you have basically a times 1 divided by a is equal to 1 divided by a times a. And so what that means is that well, multiplication is a binary operation on for example, whatever set you are talking about here. And then you can say that 1 divided by a is the inverse of a, or you can say that a is the inverse of 1 divided by a. But now suppose that a belongs to the set n, and we are talking about the multiplication operation, and also a is not equal to 1. That means that a has to be greater than 1, because we are talking about the set of natural numbers. So let's say that a is equal to 2. Now, for a is equal to 2, 1 divided by a has to be equal to 1 divided by 2, which does not belong to n. So then you can say that, then of course you can say that 1 divided by a is not the inverse of a for the multiplication operation on n, because and it's basically simply because 1 divided by a does not belong to n in the first place, so it cannot be the inverse of a for that operation with respect to that operation, right? Now, I talked too much about this example, and that was because I hadn't understood this definition, and that basically and that basically happens almost all the time. And when that happens, what you will notice is that you will not be able to solve a certain problem or understand a certain exercise or problem. And then what that tells you is that there is something in the definitions or in the concept that you haven't understood. And then you have to go back to the concept, to the definitions, read them again until you know where your problem is. And usually, basically, you know what you don't understand, you know it. You know what you don't understand. So you can basically go back and see what it was that you didn't understand. So now going back to the solution of this problem, number 40, we can say that solution 40, we can say that show that since negative a does not belong to n, so you can say that since negative a does not belong to n so then negative a cannot be the inverse of a for addition operation on n. Cannot be the inverse of a for the addition operation, on n. Although negative a satisfies negative a plus negative a is equal to 0 is equal to negative a plus a. Although it satisfies this equation, Well, but it doesn't exist in n, meaning that, for example, if you take your a as 2, then negative 2 does not belong to n, so it cannot be the inverse of a for the addition, basically, for the addition operation on n. And similarly for a not equal to 1, similarly for a not equal to 1 in n, for a not equal to 1 in n, 1 divided by a does not belong to n, which implies that other than 1, which implies that other than 1, no element of n has inverse of multiplication operation on n. No element of n has an inverse of, has the inverse 4 multiplication, I should say, the inverse 4 multiplication operation on n. And then as a note here we have examples 34, 36, 38, and 39 show that addition on R is commutative and associative binary operations with 0 as the identity element and negative a as the inverse of a in R for all a. So, well, we didn't know this. Of course, this was a broad generalization based on all of those examples. But then you can say that examples 34, 36, 38, and 39 show that addition on R is commutative. Show that addition on R is commutative and associative binary operations with the 0 as the identity element, with 0 as the identity element, and negative a as the inverse of a, and negative a as the inverse of a in R for all a, right? So what that means is that addition, basically these examples show that addition on R is commutative and associative binary operations with 0 as the identity element, and a negative a as the inverse of a in R for all a, basically belonging to R. So that was basically that was all of the theory that we had here, and all of the definitions and all of the concepts that we needed in order to do exercise 1.4. Here we have 13 exercises, And then after that, we have a couple of miscellaneous examples and miscellaneous exercises, and then the theory and concept. That means that the theory and concept in this basically chapter or in this course are over. We will work a little bit with everything that we have worked with or everything that we have learned, and then we will basically finish this chapter up with all of those exercises and examples. So I'll see you in the next video, and thank you.